All right, so this lesson is about inverse functions, and I want to remind you of a few things. First, a function is the definition of a function is each input has one output, and a lot of times we use the vertical line test to test for what a function is. And there are some common inverse functions that you know about. So, for instance, addition and subtraction are inverse functions. Multiplication and division are inverse functions. You also know that like the square root is the inverse function of something squared, right? That's how we're thinking about undoing things. Ones that you learned in geometry. So you would take the sine if you knew like the two sides. But remember, if we don't know the two sides, you used to use that button, and you can look at your calculator now. There's a little button that has the little -1, okay? The same is true like for cosine and tangent. Oh, sorry. Cosine. Okay, so you know a little bit about inverse functions, but we know these are like very simple. These are more like inverse operations. They're very, very simple. So what we're going to talk about today is when we have more complex functions, how to find their inverses and also what that means. So a few things about inverse functions. So the first thing, and to some extent you're going to want to copy these. The first thing is that inverse functions change. They like switch basically the input and the output. So make sure that you have that written down. Inverse functions switch input and output values. And so we can see that here in this mapping, right? In the original function, A went to 3, like A, B, and C are going to 1, 2, and 3. And then when we do the inverse, it switches. And now 1, 2, and 3 are going to A, B, and C. Okay? And then we can look at this one, this middle graphic. It just kind of shows you, so a few things I want you to note, and you should write all of these down. A few things that I want you to note here. Original function notation is f of x. Inverse function has this little -1, and that should remind you of that little -1 that we saw on the sine function. And notice that it switches like the x and the y values. So what was once x now becomes y, which means if it was the domain, now it's the range. And opposite, what the y value becomes x. So what was the range on the original function is now the domain on the inverse function. Okay, and so what that looks like graphically is it is going to look like a reflection. And so you should write this down also. This is inverse functions create a reflection over the y equals x line. And so you can see here, you can see it, right? This is like a direct reflection over those two lines, over that line. And the reason that should make sense to you that it is a reflection, because the whole purpose of an inverse is that you're replacing output values, y values, with input values, x values. So your points are just going to reflect across this line. So this first example, we're going to find the inverse of linear functions, because that's what you're going to see more often than not. So just like we said with the definition, we're going to switch where the inverse, the function itself, and the x is. Notice everything else is going to stay in the same place. So I'm going to switch those two. This is going to be x equals. The -2 is just going to drop down. And then I'm going to write my inverse notation right here, -1x plus 10. So take a second to make sure that you understand everything has stayed in exactly the same place that it was, right? The function and the x have switched, but the equal sign, the -2, and the plus 10 have all stayed in their same spots. All right, so now my goal as I'm solving this is to get this f of x piece by itself, which means I'm going to need to get rid of the -2 in the front and the plus 10 at the end. So now I'm just solving this. I'm going to subtract 10. I can't actually do x minus 10 and get any specific value. So when I do x minus 10, that's going to give me just the value x minus 10 equals -2 times the inverse. And then I'm going to need to divide by -2. Sorry, I'm trying to switch colors here. So I'm going to divide by -2. And that's going to leave me my inverse function by itself, which is going to make my final answer. Now, here's the thing. You can leave this as what you see right here. So it is possible to leave this written just like this. However, Delta Math is going to want you to usually input it in slope-intercept form because it is a linear function. So let's practice that. So that just means we need to look at these as separate pieces. Let me go back here. Am I highlighting? Okay, so we're going to first divide the -2 right here. That's going to give me -1/2 x because there's a 1 in front of the x, right? And then I'm also going to divide -2 on this side. So that's -10 divided by -2, which is +5. And that is what my inverse function equals. And that should make sense that we're getting an equation because we said it is an inverse function. It's not just a specific value. Okay, so we're going to start this next example in the same spot. So remember, my first step is to switch. And you all might even write a little star on the notes, your notes off to the side that reminds you that your first step is actually going to be to switch those two. All right, so this should say x equals 2/3 times the inverse minus 12. So my first step here, hopefully you all can see, is going to be to add 12 to both sides. It's going to leave me with x plus 12 equals 2/3 times the inverse. And then there's a few different strategies for how to get rid of this 2/3 right here. Usually I just try to get rid of each part separately. So I'm going to get rid of the 3. So to do that, I'm going to multiply everything by 3. Because in a fraction, this means divide by 3. So if I multiply by 3, it'll cancel. Okay, so that's going to leave me with 3x plus 36 equals 2 times the inverse. And now you might notice we're exactly the same place that we were just a second ago. I just need to divide by 2 here. And since I know I'm going to have to do this separately anyway, I'm just going to write it separate. Okay, this is going to leave my final answer as 3/2x plus 18 equals the inverse. Okay, those are 2 good examples of linears. Let's do one example that's a non-linear inverse just so that you see kind of what that looks like. So for this example, we're going to start in the same place. We're going to switch the f of x and the x and use our inverse notation. So this is going to be x equals parentheses 2 times the inverse minus 5 squared. So again, remember our end goal. We're trying to get this inverse piece by itself. So now I'm not only going to have to get rid of the 2 and the 5, I'm also going to have to get rid of this squared right here. So remember the to undo squared, you might remember this from Pythagorean theorem, we take the square root. So I'm going to take the square root of both sides. And so that's going to leave me with the square root of x equals, the parentheses aren't there anymore because they were just for the squared. So 2 times the inverse minus 5. Okay, so now we are going to need to work this out the way that we did just before. So we're going to add 5 to both sides. And just like we did once before, this square root x and the 5 are separate. So this is going to be the square root of x plus 5. Sorry, I'm writing with my finger, y'all, so this is not showing up super well. 2 times the inverse. And when we have square roots or other more complex functions, we're not going to divide them out separately because that gets a little bit complicated. So we're just going to divide the whole thing by 2. So for this problem, my final inverse is going to be the square root of x plus 5 over 2 equals the inverse function. And the last thing I just want to point out on this one, just so that you see the difference, is that for this inverse function, this plus 5 is outside of the square root symbol. So the square root symbol does not extend over the whole thing. There will be times that it does, but in this instance it does not, because they were, if we look right here on the left, those things were 2 separate values to begin with.